Welcome to week 6. We will cover this and next week another exciting topic in image and video processing, the topic of recovery. It's a natural continuation of image and video enhancement that we covered last week. There's an important distinction between the two topics. As we saw last week, the objective of enhancement is to improve the visual quality of an image or improve its usefulness in performing a certain task based on some subjective criteria. For image and video recovery problems, information is lost either in the spatiotemporal or the frequency domains, and the objective is its recovery. Unlike enhancement, however, where also information is lost in some cases, in recovery, a model of the process that resulted in this information loss is first established, and then an objective optimality criterion is determined based on which an estimate of the original image is sought after. During this week, we'll provide examples of image and video recovery. Depending on the application domain, recovery comes with different names such as restoration, deconvolution, error concealment, in painting, blotting artifact removal, super resolution, punch sharpening, and so on. All these recovery problems are inverse problems. We will then discuss some of the important restoration approaches that are used widely in practice. There is probably no application area where images and videos are acquired that does not have either active or potential work in image recovery. The material, therefore, of this and next week will be very valuable in this regard. In this module of the course, we will first show examples of image recovery. Then we will focus on image restoration and more specifically image deconvolution approaches, and we'll group them into deterministic and stochastic. And finally, we're going to show the formulation of other recovery problems. I use the term recovery as the umbrella term. Any problem in which information is lost and needs to be recovered. As we'll see, recovery problems assume specific names based on the application. Restoration typically, and deconvolution as a special case of restoration, refers to a specific modeling of the input-output relationship of a degradation system. We show here a blurred image due to defocusing. This is the situation where the automatic focusing system of a camera failed or the manual focusing was not successful. So what is acquired is this blurred image. It's hard to decipher what's in it. So applying a restoration algorithm, we can obtain a restored image that looks like this. This is, by the way, a grayscale image, not a binary image. So on the left was the image of ECS department at Northwestern before I joined, and on the right is the image after I joined. The Hubble Space Telescope, named after the astronomer Edwin Hubble, was placed in orbit in 1990 by a space shuttle, and it's still in operation. Between 1993 and 2009, 5 different repair missions repaired, upgraded, and replaced systems on the telescope. Now, after it was placed in orbit, it was discovered that its main mirror was not cut to specifications, and therefore the telescope was myopic. It could observe images such as this one of Saturn, and this is a blurred image. The rings are not clear. So these images would be beamed down to stations down to Earth, and people would try various restoration algorithms, like the ones we'll be discussing later in class, to obtain restored images. Based on some work we did, here is a restoration of Saturn. The rings are now much sharper, and accurate flux measurements can be made on the restored image. This is another observation by the telescope of a galaxy, and here is the restored version of this particular image. I should mention that in carrying out the restoration, the impulse response of the degradation system, which is the myopic telescope, needs to be known. And in this case, either this impulse response will be obtained based on geometric optics or would be obtained by pointing the telescope to a distant star and measuring the response to that. So the star represents an impulse, therefore this is the impulse response. The telescope actually has been extremely successful. It has acquired beautiful images of the heavens, and major scientific results have been obtained due to its observations. Here's a color image, and this color image is undergoing degradation that is three-dimensional. So in distorting one channel, the other two channels have a role in it. So due to this three-dimensional degradation, the degraded image looks like this. It has been subjected to color alterations. So therefore, a three-dimensional deconvolution is required, and here is an example of the restored image. When the degradation is 3D, then the deconvolution is certainly 3D, but in many instances the degradation can be two-dimensional, but still we might choose to do a three-dimensional deconvolution by taking, in other words, the other channels into account. This could be thought as a multi-channel restoration. And actually there are a number of applications in microscopy, for example, fluorescent microscopy, where 3D deconvolution is required. Here's an example of a blurred image due to motion between the camera and the scene. It's an aerial picture taken by a plane, and the motion compensation system on the plane failed, and therefore this blurred image was acquired. This is a real image of a toy train, moving toy train. Due to motion again, there is blur on the train, while the background and foreground are not blurred. So in this particular case, a smart algorithm is required to first identify the parts of the image, the pixels in the image that are blurred, and restore only those pixels while the remaining of the image stays untouched. Here's an image of a so-called autoradiograph. Microspheres are attached to a specimen, and then this radiographic image is acquired. It's certainly blurred. Applying some of the algorithms we'll be discussing in this class, here are the restored versions of these images. So the blurred images, the restored images. Clearly a lot of information has been recovered. We can see the fine details on the aerial image. There's a river there and the bridges. We can see the microspheres well defined, and we can see the image of the train being now sharp. We can read the letters on the side of the train, while the foreground and background are also sharp, have not been modified, have not been degraded by this operation. We show here an image acquired by a handheld camera. During exposure time, the camera shook, and this is the resulting blurred image. We show some sub-images here blown up to pay attention to. The degradation is not known, and therefore a blind, spatially varying restoration algorithm was developed by us and applied to this image to obtain this restoration. We see here the shape of the degradation, of the impulse response of the degradation, and we also look specifically at these sub-images, so the improvement is crystal clear, and you can see the three people here walking. They're not distinguishable at all in the original observation, but after restoration there's a very good representation of them. As we will see when we discuss later in the course in detail image and video compression techniques, in carrying out compression, we take each still image or frame, subdivided into blocks, and then each block is compressed independently from the remaining of the blocks. So due to this specific type of processing, especially at high compression ratios, if one looks at the compressed image, one can see those annoying blocking artifacts. You can see here the boundaries of each and every block this image was divided into. So the problem at hand is to devise a recovery algorithm that will bring back some of the lost information and result in removing these blocking artifacts. So here is one result we obtained with one of the algorithms. By and large, the blocking artifacts have been reduced or completely eliminated. Maybe if one pays attention at the forehead of the lady, and maybe at the hat here, and some other regions of the image. This is the same problem as in the previous slide. Here we deal with video, not just a still image. So the blocking artifacts are visible in this frame of the video. And based on a technique we also developed. This is the processed image. In this particular case, when video is involved, one can utilize not only the spatial information, but also the temporal information based on motion information. You can find the similar blocks, the similar regions in previous frames, and utilize that information to remove some of the blocking artifacts. Here's another example of a recovery problem. When images and videos are transmitted, rows of macro blocks are typically placed into packets, and these packets are transmitted. If some of these packets are lost during transmission, then the received image can look like this. This is a frame of a video, and these black here rectangles indicate packets which were lost, and therefore the intensity information is lost. So we try to recover the lost information. This is a recovery problem that is typically referred to as an error concealment problem, since we try to conceal the errors that were introduced by the channel. Since we deal with video again, one can use not only the spatial neighborhood information to recover this lost information, but also the temporal information. Based on some of our work, here's an example of a concealed frame. It's a satisfactory result, especially for this packet here, since a lot of structure was lost, but we see that it's recovered nicely. This particular packet did not convey probably as much information, but still it's a satisfactory concealment. Here's another example, is a still image. So these blocks were lost, the black blocks. This could represent the Bersty type of error. So based on a different algorithm, recovery algorithm that we developed, here is the recovered image. It's almost perfect. If one pays close attention, there are some issues like here, for example, or here, which might be part of the hair and so on. But by and large, is a very satisfactory concealed image. The last example we saw transitions nicely into the in-painting problem. So here we're given an image like this. This is actually an old movie, and these were supposed to be subtitles. But back then, when people were not as skilled readers, and these subtitles were rather large. So this is the only copy of the movie available, and we want to remove the letters so that the original information is available. So this problem is again referred to as in painting. We want to paint the missing values inside the image. It's very similar to the error concealment problem. One difference is that in error concealment, the missing regions are nicely structured, and their location is known. With the in-painting problem, one first has to identify the regions in which information is missing. So in this particular example, we have to identify each and every letter and realize that wherever this is white here, it's a letter, is information lost, but there's white shared here, and the information is not lost there. So this is not an easy problem that has to first be solved before in painting. So here's an example of a not very skillful and successful in painting, but nevertheless it gives you an idea of the problem. The letters are removed. Again, in painting can be applied to still images or videos. When video is available, then there is both spatial and temporal information that can be utilized towards in painting. Another recovery problem is the image super resolution problem. We observe a set of low resolution images, and the objective is to combine them in order to obtain a high resolution one. So these are images of the same scene, and there is a transformation connecting them. The transformation could be a simple subpixel shift among the frames, or a rotational component can be there, or any, in general, arbitrary transformation. So based again on some of our work, here is an example of the super resolved image. None of the numbers is visible in the low-res images, and clearly a lot of information was recovered, since the numbers can be read and the image is sharp and of high resolution. Here's another example for low resolution images are observed and combined judiciously result in this high resolution image. Actually, the dimensions of these images here are the same, the low and high, but this was done just for displaying purposes. The super resolution of compressed video is another recovery problem. So the degradation model is shown here. We start with a video at the original resolution. A short segment is shown here. This is downsampled by a factor of 2 in both dimensions in this particular case. And then this downsampled video is compressed using the MPEG-4 video compression standard at 1 megabit per second using a specific rate controller. So here is the compressed downsampled video. So the objective is to work with this compressed downsampled video and come up with an estimate of the video at the original resolution. So there are two results. On the left is the result based on bilinear interpolation, and on the right on an algorithm that we developed. So by comparing them side by side, it should be clear that a lot of the artifacts are not there with the so-called proposed algorithm here, and it represents by and large a very good representation of the video at the original resolution. Another recovery problem is the dual exposure restoration problem, a more recent problem. According to it, 2 images are observed, a long exposure image and a short exposure one. And there are actually cell phones in the market that do that. They take simultaneously 2 images, a long and a short exposure one. So the long exposure one is subject to blurring due to motion, shaking of the camera, and so on. The short exposure one does not have this problem, but it is noisy and also the colors have been altered. One approach would be to work with a short exposure image and smooth the noise, and if we do so, we obtain an image like this. It's brighter, the noise has been removed, however the colors are not the colors of the original image. If we combine now the long and short exposure based on some of our recent work, we can obtain the restored image shown here. So this is definitely an improved version of the observations. Is a sharp image while maintaining the colors of the original scene. Blind restoration was performed, and this is the estimated point spread function or impulse response of the degradation system that gave rise to the long exposure image. Another recovery problem by the name of punch sharpening is encountered in multispectral imaging, in remote sensing, when images are acquired, for example, by Landsat. So in that case, instead of having an ideal sensor that would generate high-resolution multispectral images, instead there is spectral decimation as well as spatial decimation. So the spectral decimator results in a high-resolution image, but the frequency information has been lost. It's a grayscale panchromatic image, while the spatial decimator will give each and every band of this multispectral image, but at a reduced resolution. So the problem at hand is to combine the panchromatic high-resolution image and the low-resolution spectral images and try to increase the resolution of the spectral images, bring them to the resolution of the panchromatic image. It's a super resolution problem, but in this context of multispectral imaging is referred to as a punch sharpening problem. So here's an example of punch sharpening. We're given the low resolution spectral, the panchromatic grayscale, and combining the two, here is a punch sharpened image that we obtained with one of our algorithms. So it has the same resolution as the panchromatic and has all the spectral information. Here is shown clearly in pseudo-coloring of the spectral bands. Another recovery problem is that of demosaicing. Most modern digital cameras acquire images using a single image sensor overlaid with a color filter array. The most commonly used one is the Bayer CFA, shown here. According to it, 50% of the pixels are green and 25 are red and blue. So equivalently, out of the three planes, the R, G, and B planes, 75% of the pixels are missing here, 50% in the green channel, and 75% in the blue channel. So demosaicing is the digital image processing recovery problem used to reconstruct a full color image from the incomplete color samples that is shown here. With this final example, I want to make the point that a degradation such as motion blur is not only important to be removed so as to visualize the restored image, but it needs to be taken into account when another task is performed, such as tracking. So we see here a popular and successful tracker by the name of MinShift failing to perform really well when there is motion blur. The red window shows the tracking result. So the red window stays with the object most of the time, but at a number of occasions does not coincide with the object, so the tracker loses track of the object of interest. But by taking the motion blur into account, with some of the work we did here, we can see that now the tracking is more successful. This red square, rectangle rather, stays with the object most of the time. We tried to demonstrate with the previous examples that there are various sources of degradation which result in loss of information, and therefore a recovery problem needs to be solved. It's probably safe to say that whenever images and videos are acquired, there is either active or potential work in solving a recovery problem. Drawing from the previous examples, here are some examples of degradation. The degradation can be due to motion between the camera and the scene, either unintentional motion or when a motion compensation system fails, for example. Due to atmospheric turbulence, whenever we image, for example, with ground-based telescope, the objects in the sky, we have to image through the turbulent atmosphere. Due to autofocusing, either because the autofocusing system failed or when we manually focus, we don't do the best possible job. Generally speaking, due to the limitations of acquisition systems, the finite resolution, for example, imposed by the optics, constraints imposed by physics of the objects of interest we want to image, and cost considerations. Very often we want with software to increase the capabilities of hardware. So we want to make, for example, a $1,000 camera perform like it's a $30,000 camera. Due to the finite resolution of sensors, and this resolution is dependent on the frequency of the electromagnetic spectrum at which we are imaging. Due to quantization errors when, for example, compression is performed on a signal. Due to transmission errors introduced by the unfriendly channel, and of course the ever-present noise. We show here a list of the recovery problems we described through the examples we just showed. So there's the ever-present noise smoothing problem, restoration or deconvolution in 1 or 2 or 3 dimensions, removal of compression artifacts, super resolutions in its various incarnations such as pan-sharpening or demosaicing, the 2 Kazan problems of in-painting and concealment, dual exposure imaging, reconstructions from projections, and these 2 topics that we did not show any examples, but we will visiting them later. I'd like to mention here that some of these problems are combined. For example, I might be interested in solving a super resolution problem with compressed images or videos, when of course noise is always present in the data. Another comment is that in some applications we observe just a single image or frames of a video, but while in other applications there are multiple observations involved, such as the dual exposure or the super resolution. The examples of discovery problems we described and additional others can be encountered in a number of applications. For example, in space exploration or images acquired by the Hubble Space Telescope, remote sensing, surveillance, medicine, neuroimaging, non-destructive testing, commercial and digital photography, video printing, printing one frame from a video, microscopy, molecular and cellular imaging, and multimedia communications. And of course, this is not an exhaustive list of either the applications or the type of recovery problems or the list of degradations we just mentioned. So this is a very, very rich field, and what we'll try to do is just demonstrate and describe some of the very basic principles that one can take then and apply to all these, again, incarnations of the recovery problem in the very many applications that such recovery problems can be encountered.